The topic of this lesson is heat energy. I said it in an earlier video, but I think we could even go farther and say for centuries, heat energy wasn't very well understood. That's why the unit of energy, joules, was named after James Prescott Joule. He kind of figured out some of the intricacies of heat. When we talked earlier, we related motion or movement to work and energy. Things wouldn't just speed up on their own. They wouldn't just magically get more kinetic energy. You would have to do work or use energy to make that happen. Similarly, we related gravity to work and energy. Things just don't magically move upward. If you wanted something to be in a higher position, you would have to do work or use energy. By that logic, there's a similar connection between temperature and work and energy. Things don't get hotter on their own. If you want something to get hotter, you've got to do work or use energy. If we think back, I don't want to scroll too far. If you think about kinetic energy, we've already got the equation, but now that we have the equation, we can sort of backtrack. It kind of makes sense that if we're trying to make something move, how much work or energy we have to expend to do that, how much energy we've got to use, how much work we've got to do. It kind of depends on how massive the thing is, and it kind of depends on how fast you want to get it going. So since it depends on mass and the velocity, you can expect mass and velocity to be in the equation. We did that work energy theorem equation, and we got the 1/2 mv squared, work energy theorem derivation, and when we did that, we got this 1/2 mv squared equation. Similarly, we can reflect on gravitational energy. If we're thinking about the work it would take to lift something, it's going to take more work to lift something that's heavy or massive, and it's going to take more work if we want to lift it really, really high. So we can expect, just by intuition, mass and height to be in the equation. After our little derivation, the other lesson, it works out that the gravitational energy is mgh. It's not a proof, but just thinking. Let's do the same sort of thing if we wanted to heat something up. To help, let's use our imagination a little bit. What if we had like a battery-operated device? Maybe you're camping, or maybe, I don't know, you got just this sort of magical device. It's powered by batteries, and when you touch objects with it, doesn't matter if the objects are solid, liquid, or gas, but when you touch things with it and turn it on, it heats up the thing that you're touching. What would drain the battery more? What properties of the object that we're heating would make it take more energy to heat that thing up? So not a proof. I'm really just trying to get you to use your imagination. If we had to guess what's in our equation for heat energy, what do you think would show up? In kinetic energy, by thinking, we kind of knew there'd be a mass and a velocity. For gravitational energy, with some thinking, we kind of knew there'd be a mass and a height. If we think about heat energy the same way, what do you think will show up in the equation? What would take more energy to heat up than, say, something else? All right, if you haven't had a chance to think about it, I'm going to scroll down. So if you want to think about it a bit longer, pause the video. But here's the answer. Here's the properties that affect heat energy. I'm going to go a little bit at a time for some drama here. There are 3 of them. Usually when I do this in class, people come up with 2, and the third one's a little bit weird. But one property is how much mass. If you needed to heat up a swimming pool, actually this quadmester, it's that kind of time of year. If you've got a pool and you're heating up a pool, you should hopefully know, or maybe your parents know better, it's going to take a lot of energy to heat up a swimming pool, as opposed to, say, me heating up a cup of water for my coffee in the morning. It's both water, but if you're heating up a whole swimming pool's worth, that's going to take a lot more energy than just heating up a little bit. So expect M to be in the equation. The other factor is how hot you're actually heating it. Kind of like the height in gravitational, it would take a little bit of energy to lift it a little bit, take a lot more energy to lift it a lot higher. Kind of like speed, take a little bit of energy to make something go slow, take more energy to make it go fast. Same logic here. It would take less energy to heat it up a little bit than to heat it up a lot. We're going to denote temperature with capital T, and because we're really worried about or concerned about the change in temperature, we're going to write it as delta. So the triangle is delta, delta capital T. That's going to be our notation for change in temperature. If we start off with pool water at 24 and we want to get it to 25, that's not going to take, well, it's going to take a lot of energy, but not a ridiculously a lot amount of energy, as opposed to if we started with a pool at 10 and we wanted to get it to 25. The bigger the change in temperature, the more energy it takes to make that happen. The third factor isn't quite as obvious. The material comes into play. Some things just are easier to heat up, take less energy to heat up than others. Classic example is imagine, actually another good timing is starting to warm up outside. Imagine we did like a little class road trip to the beach. On a sunny day, the sand gets hotter before the water. In geography class, grade 9 geography, great class, you learn that water moderates the climate. Water is a special material for a whole bunch of reasons, but one of them is it really takes a lot of energy to heat up water. Just the chemistry of water, it doesn't heat up as easily as, say, like tin or solids. It doesn't heat up, it takes more energy to heat up water than other liquids. It's just a weird thing about water. But bottom line is the material that you're heating up also affects how much energy it takes. The quantity that we use to sort of specify the material, it's called specific heat capacity. It's got the short form of capital C. Specific heat capacity, it's almost like density or other like conductivity, like other physical properties. It's a number, and it's how many joules it takes to heat 1 kilogram of that material by 1 degree Celsius. So water, the value for water is approximately 4,200. That's water's specific heat capacity. So if you had a kilogram of water in like an electric kettle, if you plug that kettle in and wanted that 1 kilogram of water to get warmer by only 1 degree Celsius, it would take 4,200 joules of energy to make that happen. If you Google it, specific heat capacities of metals are usually much lower, like iron, I think, is like in the 300s. So if we had a clump of metal, if its specific heat capacity was 300, that means it would take 300 joules to heat that particular metal, to heat 1 kilogram of that particular metal by 1 degree Celsius. If you had a fraction of a kilogram, it would take a fraction of the specific heat capacity. If you were heating it by 2 degrees, you'd have to double the specific heat capacity. Heating it by 10 degrees, you'd have to multiply by 10. When we put it all together, and again, you don't need to really totally be comfortable with how we got the equation. You just have to be able to work with the equation. But hopefully it clicks. Heat energy is the mass of the object, as we expected. This thing we call specific heat capacity, which maybe we didn't expect but is important, and the change in temperature. That's the order that it normally gets written, and I can't give you a great reason, but sometimes you see it in chemistry, so maybe if you've seen it in chemistry, this shouldn't be a total surprise. For some reason, I'm blaming chemistry people. Instead of calling it like capital E with a H for heat energy, they called it letter Q. It's still an energy. We could call it capital E, but everybody calls it Q, and it's got the equation mc delta T. That tells us how much heat energy it takes to heat something up. I'm going to pause the video soon and run a second one for the second part of the lesson, but just a couple little things. Take a look at this one. Well, actually, let me scroll back. Q equals mc delta T. There's 4 parameters, 4 properties in that equation: the Q, the M, the C, and the delta T. If I tell you 3 of them, you should be able to calculate the 4th. So in example 1, I've told you that M, because I've told you it's water, you know the C. I've told you the 2 temperatures, so you can do a little bit of subtraction to find the delta T. You know 3 other things, you can calculate the Q. Number 2 is basically the same, just I switched up the material. The last little piece, and then I'm going to pause, is what's cool about heat and what was misunderstood is it follows the conservation of energy exactly the same way as gravitational and kinetic energy would. If you take something that's hot and drop it into some cold water, so sort of classic blacksmith kind of work. Let's say we got a hot chunk of metal and we drop it in the cold water. The hot metal is going to lose energy as it cools down. So we could do an MC delta T calculation for the hot metal, and as it cools down, since it's cooling down, its delta T ends up being a negative number. If we drop it in water, the water is going to heat up in response to that hot metal. If we do an MC delta T of the water, it's going to be a positive number. So the thing that's losing energy ends up having a negative Q. The thing that gained energy has a positive Q. Since energy is a conserved quantity, if the hot metal lost, I'm just going to make up a number, 200 joules of energy, those 200 joules of energy had to go somewhere. They're going to go into the water, and the water is going to get warmer by 200 joules. You can almost think of it like a bank account thing. Oops, I wrote that backwards. That's not good. The thing that loses energy is going to have a negative Q. The thing that gains energy is going to have a positive Q. So let's say you're doing some business work at one account, you transferred money from one account into another. You would see a deduction or a negative in your one account and a positive in the other account. We always have to be able to account for our money, so if you took $100 out of one account, we should see a positive 100 in another account. That maybe didn't come out so great of an explanation out loud, but take a look at this example, watch that little video clip, that kind of does a better job of explaining it. There is a part 2 to heat energy, so this is where I'm going to pause this video. Basically, heat energy is MC delta T. C is this cool specific heat capacity. If you think back to grade 9 science, it's a physical property. Each material would have its own C. And if I tell you 3 of those things, you should be able to calculate the 4th. And since heat is an energy, it's also conserved, so we can do some cool stuff with conservation of energy. That's where I'll pause this one. Work through the examples. I think there's a worksheet linked at the bottom of the document. You can look at the first couple questions off the worksheet, and then the second video will explain part 2 of this.